So my name is Martin Saveski. I'm a graduate student at MIT, and this is a work I did during my stay at Amazon in Berlin last summer. These are some. I will be talking about one-pass ranking models for low-latency product recommendations. These are the people I worked with, my collaborators. Antonino was the mastermind of this work, Rodolphe, Jenatton, and Cedric Archambeau. So I suppose all of you have been to the Amazon product webpage. Every time you open a product webpage on Amazon, you scroll down and you will see this widget, which says that if you bought these people who bought this item also bought some other items, and then these are listed. So then every time you click on this, all this is logged into the system. And the question we are interested in is how we can make use of these purchase logs to improve the recommendations. So it's a classical ranking problem. We have, as a context, we have the context in which the user is, we have the product, and then we are interested in ranking the most relevant items to the top. There are several other widgets. For example, there is the recent history footer where we look at the things that you bought last, and then based on that, we suggest some other items. So unlike usual, this time the problem came with slightly specific constraints. So one is that the dataset is very large, both in terms of number of dimensions, but also in number of examples. There is a constant drift in the distribution. There is all kinds of seasonalities in the data. People buy differently on Mondays than on Fridays, and differently on usual day, differently on Black Friday, and there are all kinds of seasonalities. And then we have to have real-time ranking. If the user waits for 1 minute to get the recommendations, then it's not of much use. So it has to be very fast. In practice, this means that we have to have very small memory footprint. We cannot really load the data in memory. So every method that basically runs in-memory learning is not an option. To account for the drifting distribution, we have to have fast training time so that we can retrain often. And then to have real-time ranking, we really need a model that will do low prediction latency. So just to give you a gist of our approach, and then I'll unpack that in the following slides. So to achieve small memory footprint and fast training time, that makes a great candidate for stochastic optimization. And we show that one pass and learning with only one pass through the data is enough to achieve satisfactory performance. And then to have a low prediction latency, we impose sparsity. We learn very sparse models that allow us to do very small number of computations in prediction time. All right, so before I go into the details of the loss function that we use, I will kind of introduce some of the design decision one has to do before deciding on a ranking function. Probably most of you know there are 3 broad families of ranking functions, pointwise, where you have score vector. You take the features of the function of the product, and then you run through your scoring function, and then you get some score, and then you sort them based on the score that you got. However, you're kind of asking your algorithm to solve a problem that harder than what you really want. You don't really care whether item 1 is 10 times better than item 2, but you really care about the order. So pairwise approaches kind of fix this problem by casting the ranking problem to a binary classification problem, saying whether item I should be ranked higher than item J. However, they miss another important thing, which is they don't really distinguish between items that are on the top versus items that are on the bottom. So if I get item 1 and item 2 wrong, that should cost me a lot. But if I get item 90, 99, and 100, that should not be that important. And list-wise approaches do exactly that. They take the whole list as an object for optimization. Another important design decision is the kind of loss function you choose. Many times we really care about the evaluation function. For example, when we have ranking, that may be NDCG. But those functions are really hard to optimize for directly. They're discontinuous, and it's very hard to work with them. So what we do usually, we will pick some surrogate, which we hope, as we optimize, will drive the evaluation function too. For example, that we do this all the time. When you do classification, you may care about F1 measure, but what you're really solving may be some logistic function. Okay, so Having all these considerations in mind, we chose a loss function called lambda rank. It was published in 2007 by Burgess and Nips. The idea behind lambda rank, it's a list-wise approach, so it takes the whole list into account when we optimize it. And also it implicitly optimizes for the evaluation metric we care about, but still gives us a convex function. So let me walk you through it. Suppose we have one list of 4 products, and each of them is associated with some feature vector, x1 to x4, and then we have the ground truth rank. We know that the first 2 products should be ranked higher than the second, and the third and the fourth, and then the fourth should be ranked higher than the third should be ranked higher than the fourth one. And let's say we pick some item I and item j, and we know that item I should be ranked higher than item j. So we'll define 2 quantities. The first one is delta m, which is where m is some metric we care about, for example, NDCG. And then we measure what will be the difference in NDCG if we switch I and j. So in other words, how much it will hurt our evaluation measure if we got I and g wrong, if we got the sorting incorrectly. And then the second one will be kind of the difference of our scores. If we got I and j right, then the second term will be actually bigger than the first one, and then we will not suffer any loss. If it's the other way around, then we have to pay some loss. We do this, we iterate over all pairs such that I is always ranked higher than j, and if we make a mistake here in delta s, then we pay proportionally to how important it was to actually get those 2 right in terms of our evaluation function. So notice here that actually the only optimization parameters are here, the W's, and we don't really need to, we optimize for the NDCG implicitly, or whatever metric we're caring about. So that makes lambda rank really appealing. As I mentioned, so to actually get low prediction latency, we impose additional 2 constraints. We add L1 and L2 penalties governed by 2 hyperparameters, lambda 1 and lambda 2. Both of them implicitly control the model complexity. Lambda 1 trades off between sparsity and performance, and lambda 2 essentially adds some strong convexity and improves the convergence properties. So this formulation in terms of classification usually is called elastic net. Most of you have probably heard of it. So from now on, I will kind of define it as elastic rank, and I will refer to it by using this name. So to optimize it, we used a few extensions of stochastic gradient descent. It turns out that optimizing for the L1 is slightly trickier because it's discontinuous. People have done some work on this before. We tried using Phobos due to Dookie in 2009, which basically does a gradient step ignoring the L1 norm, and then after that does a small proximal step which finds a slightly sparser solution. And then the other approach we tried is that RDA, or regularized dual average, due to Chow, 2010, which has slightly different approach. It keeps an exponentially weighted average of the gradients and then solves a proximal step that involves this average. And finally, we tried just a very simple heuristic, which basically every k steps, we will scan our weight vector, and if there is a value with the absolute value lower than a threshold, then we will set it to 0. Very simple heuristic. No guarantees. The first 2, there are some very interesting theoretical guarantees. Before I share the results with you, I want to just share the way we kind of did these hyperparameter optimizations. So many times, as you saw, so you have lambda 1 and lambda 2. These are all hyperparameters you need to choose. You also need to adjust for some learning rates and so on. And many times you need some knowledge in machine learning to do this. However, when you deploy in industry, not all teams have this kind of experience, so it's nice to provide an interface which will actually automatically adjust the parameters. So what we would usually do would be we will define a grid for each of these parameters, and then we will do kind of brute force cross-validation. In this case, we implemented a Bayesian approach that kind of keeps a model of all the parameters we chose, and with only much fewer tries, we were able to actually converge to the right parameter settings. There are more details in the paper. All right, so Then next we thought, okay, we kind of constrained the algorithm. We added so many constraints. We do only one pass. How will that influence the performance? So we took the public datasets from the LETOR benchmark. This is a classical document retrieval dataset, and then we compared one point-wise approach, logistic regression, one pairwise, SVM-rank in green here, and then listwise, which is a listwise method, and then ElasticRank. So here on the vertical, you can see NDCG at 5. We let all the other algorithms run until they converge, and we do only one pass with ElasticRank. So essentially, you can see sometimes we win, sometimes we don't do so well. There are some other methods that do better, but we are never statistically worse than the best method. So essentially, we don't lose much by adding these so many constraints. So that was encouraging, and then we tried on our purchase logs. So the data set is in the order of millions of examples. The number of features is in the order of thousands. Many of them, actually most of them, are categorical, which when you unfold them, that leads to millions of dimensions. And then we took a continuous time interval, which we divide in 11 pieces. We use 9 for training, 1 for validation, and 1 for testing in the usual way. So here are the results. On the vertical, you see recall at 1. There are 2 things to observe. So the 3 optimization methods, SGD, PSGD, Phobos, and RDA, do very similar. There is no very significant difference between them. And in ElasticRank, does better than both logistic regression and SVM, both point-wise and pairwise approach. Then we looked at how these 3 optimization approaches compare in terms of which one does a best trade-off between sparsity and performance. Okay, so here on the horizontal, you see the number of weights. So this is the number of features that we'll use. And then the vertical shows the recall at 1. So you can see Phobos is kind of not doing a good job of kind of choosing the right features. Then the simple heuristic of the pruning every k iterations does quite a good job and it's very stable. Whereas RDA, the regularized dual averaging, strikes the best balance. So as you can see, for example, with only 10 features, it is as good as using thousands of features. Okay. And then the sparsity, as I said, leads to very short prediction time. So if we have 4 features, that takes about 6 microseconds to compute the scores, 29 about 8 microseconds, and around 2000 will take only 10 microseconds to compute. What this graph doesn't show is the time that you need to actually go to disk or go to the network to read these features. If you have really sparse network, then you will need much, much less time, and these differences will be amplified, actually. So picking the right sparse features is extremely important. So before I finish, I will summarize our contributions. I explain how you can learn ranking function with only single pass, small memory footprint, and that are sparse, and that can allow you to actually scale to large data sets and retrain very frequently and have low latency recommendations without sacrificing performance. Thanks.
Okay, thank you. Now question time. Any questions?
Okay. In your experiment evaluation, you just compare some basic baseline method that, such as rank RS and listnet. But in my opinion, the most state-of-the-art listwise method is lambda mat. Do you have compared this method in your work?
So I picked few here just to visualize these results so that it's easier to present them. In the paper, we have actually compared with few other methods. Lambda mart is not one of them because it doesn't scale. You need to train a lot of trees. I don't know lambda mart very well, but my understanding is it doesn't scale that well. So as I said, one of the requirements is just you cannot do in memory, and you cannot have so many basically decision trees in memory. That's the. So plus adding sparsity on so many models will be very hard, right?
So you mean you more focus on the skill.
Yeah, that's right.
Skill
Yeah.
on
So
that,
if we
yeah.
cannot fit it in, if we
Okay.
cannot run it, then there is really, as I said, the constraints are important. So if we don't satisfy them, that's just not an option.
Thank you.
So you didn't really touch upon how, because you have this the two parameters that's controlling the L1 and L2, right? So is that part of your training that you actually, how do you choose those parameters as when you're comparing?
Right, as I said, so we usually have validation set, and we tune those on the validation set, and then finally we use that for testing.
Okay, so in production you would just keep in the same two parameters?
So let's say that we will get the logs from the last 2 days, and we'll do the same type of division. We won't need a test set, of course, and then you will use that to tune the parameters.
Okay, thank you.
Okay, any more questions?
Hi. Did you check, so you said that you had this drifting because of weekly seasonality, for instance. Did you check whether you could include that as a feature instead of retraining daily? Or
So that's a great question. So probably some of the features actually include that, but retraining is, I think, much better option, and the more you can retrain and train on fresh data, that for sure helps. Right?
But did you try to include them, to force them in there? Things like day of the week or time of the day, or?
Yeah, I mean, I cannot explain the features, unfortunately, but one can imagine that those features can be included, yes.
Great.
Okay, we might have time for one last question. So no more questions? Okay, that's great. Please join me to thank Martin for his fantastic talk.